So to start off then, I quite like to write down the values that I'm given. So we have a mass of ammonia gas, so let's call that M subscript A to equal 27.2 grams. We're also given a mass of oxygen gas. We can do that as M subscript O to equal to 25.6 grams. And we're also given a volume, let's call that V, equaling to 45 litres. And we're also given a temperature. T, well, this would have to be in an absolute temperature in kelvins. We know that there's an equation that says the temperature in kelvins is approximately equal to 273 plus the temperature in degrees, often noted by theta. And so the temperature in Kelvin in this case would be 273 plus 27, or simply 300 Kelvin. Well, using the ideal gas equation, we know that PV is equal to nRT. However, we have to use a slightly modified version for this question here, that the pressure total, I'll just do P subscript T for total there, is equal to, times the volume is equal to the number of moles total times RT. And so we can just start to determine these total values. Well, the total pressure we're asked to calculate anyway, so we can leave that as it is. Number of moles total, well, we can think that the number of moles total would be equal to the number of moles of ammonia plus the number of moles of oxygen, and we can then substitute that in. So then the pressure total times the volume is equal to the number of moles of ammonia plus the number of moles of oxygen times by RT. But what is the number of moles of ammonia and oxygen? Well, we know that number of moles is equal to the mass over the molar mass. I'm using this equation here as we're given the masses, which then leads us on to say that the number of moles of ammonia, we just write this out again, the number of moles of ammonia would be mass of ammonia divided by the molar mass of ammonia. And then that would be plus the mass of oxygen divided by molar mass of oxygen times RT. Or what is the molar mass of ammonia? Well, the molar mass is defined to be the sum of the individual atomic masses. In the case of ammonia, we would then have the atomic mass of nitrogen taken to be 14. 14 plus, well, we have 3 lots of hydrogen. And the atomic mass of a hydrogen atom is 1. And so that comes out to be 17 units of molar mass, grams per mole. And similar procedure for oxygen, we could say that the molar mass of oxygen is equal to, in this case, 2 lots of 16, the atomic mass of a single oxygen atom. And that comes out to be 32, again, grams per mole. And now we have all the data required. We can just rearrange to make the total pressure of the subject, dividing through by volume. We could then have all this in parentheses again, like before. And this time we could then put on the end RT over V. And all we need to do now is substitute all the values in that we have. We have the mass of ammonia to be 27.2 divided by the molar mass of ammonia that we calculated, 17, plus the mass of oxygen, 25.6 divided by the molar mass of oxygen, 32, times by R, the universal gas constant, 8.31, times by T, the absolute temperature, 300, divided by the volume, 45. And if you were to do that on a calculator, you get a value of 133 kilopascals. Well, I'll explain the kilopascals in a sec. That has been quoted to 3 significant figures. Why kilopascals? That's because we've been given a volume in litres. Should this volume have been given in millilitres, then we would have a value in pascals. But it is in kilopascals, as we've been dealing with a volume in litres. Similarly, if this was in decimeters cubed, then this would be coming out to be in kilopascals. If this was in cubic centimeters cubed, then this would come out to be in pascals. And we've given then that in kilopascals then, which is fine. So moving on to part B, I've just jotted down our pressure total that we've just found out to be 133 kilopascals, and I've also jotted down the molar masses that we calculated. In part B, we're asked to find the mole fraction of ammonia in the mixture. So we can say that then the mole fraction of ammonia, NH3. Well, thinking what a mole fraction could possibly suggest, if we have this as our system, we've got lots of particles in there, we're concerned about how many of those are ammonia. So we're wanting to find out then the number of moles of ammonia compared to the number of moles there are total. Well, what is the number of moles total? We did already show this in part A, but then we'd have the number of moles ammonia divided by the number of moles of ammonia plus the number of moles of oxygen, as those are the only gases in the system. We also worked this out earlier, that the number of moles of ammonia would be the mass of ammonia divided by the molar mass of ammonia, as number of moles is mass over molar mass, so we could say that then the mass of ammonia over the molar mass of ammonia, then all divided by mass of ammonia divided by the molar mass of ammonia plus mass of oxygen over the molar mass of oxygen. And we've already showed all those values before. If you were to do it on a calculator, that would come out to be 0.667 to 3 significant figures. Units of the mole fraction, there wouldn't be any units, as we could think that's moles divided by moles, which cancels. Finally, moving on to part C, we're asked to find the partial pressure of ammonia in the mixture. This might be an equation that you haven't come across before. Partial pressure is quite simply then partial pressure is equal to the mole fraction. I'll just put mole fraction times by then the pressure total of the system. And we've already determined the pressure total, 133 kilopascals, just determine the mole fraction, so then this will equal 0.667 times by 133. And if you were to do that on a calculator, then you get an answer of 88.6. What would be the units then, do you think, of partial pressure? Well, it would just be kilopascals. It's just how much pressure does ammonia exert. And that has been quoted to 3 significant figures.